Swayam Prabha. Digital India. Educated India.
So, I am going to be teaching you some basic principles of chemical thermodynamics. So, today we have two lectures, 2 to 250, 3 to 350, and then Monday again it starts at 8 or 9? 9 to 10:50 and Tuesday 9 to 10:50. In 6 lectures, I will try to condense all the basic concepts to something essential, bare minimum essential, which will be useful for you. Okay. So, my name is Dhamodharan. This is my name. So, I hail from this place. How many of you are from Nagapattinam? Anybody from Nagapattinam? Not bad. Only one. 2. So, I come from Nagapattinam. I was born in Nagapattinam. Right across from the temple. There is a tea shop. You know that? There is a tea shop right across from the. If you are from Nagapattinam, you know the Perumal temple. Right across the Perumal temple is a tea shop, directly across. Right next to this is a mess, small mess, canteen. So I was born there in 1961. At a time, there is a small house. Okay, at the time there was no medical care. In 1961 in Nagapattinam, there was no medical care. Okay, so babies had to be delivered at home, and my mother delivered me in that place. So that is my association. And there are a number of people here who are from different parts of Tamil Nadu, right? So I am from Nagapattinam. So can you quickly tell me where? So I get an idea. So your place of where you hail from, your native place, and where you are studying. Starting from you, Salem, native place. Which college? Namakkal Tangam Hospital, near Tangam Hospital, anywhere near the market, Thurayur Road, Trichy Road. Which road? Or is it towards Vangal, towards other such, Karur route, where Namakkal means what? Namakkal is quite broad. Kumarapalayam. So near Namakkal, not exactly Namakkal. Okay. Same Kumarapalayam. Chengalpattu. Queen Mary's College in Chennai. Chengalpattu, which village? Proper Chengalpattu or Chengalpattu, any village near Chengalpattu? Tiruporur. Okay. Dindivanam enna village? Any? Proper Dindivanam. Chennai. Okay.
From Madurai National College and studied at Pudukkottai Rajas College.
Pudukkottai Rajas College. Madurai, proper Madurai?
Yes, sir.
Where? Huh?
Meenakshi Amman Kovil
near Meenakshi Amman Kovil. Danappa Mudaliyar Street. Near Meenakshi Kovil means Danappa Mudaliyar Street is. Tirkuvasal. Okay.
Government Arts College,
Krishnagiri. Tirupatur near Krishnagiri. That Tirupatur or Tirupatur near Karaikudi? That Tirupatur. Namakkal. Native Namakkal means near Namakkal. What? Mohanur. Thurayur Road. That's towards Irumapalayam. Okay. Huh? Tanjavur. Proper Tanjavur or Karandai or something like that? Pattukottai. Native Thurayur. Okay, very good. Trichy district. Okay. Chennai. Okay. So, number of Salem people from Salem. Native Salem. Salem. You are also from Salem. What about you? மயிலாடுதுறை. என்னோட பிறந்த ஊருக்கு பக்கத்தில் வந்துட்டீங்க. மயிலாடுதுறை. 2 மயிலாடுதுறை. ரூர்க்கி, ஊட்டி. ஊட்டியில் எந்த இடம்? ஊட்டி இஸ் பிக், நோ? I know a lot of villages around Ooty. Okay. Uma from Nilgiris, again Kunnura, Nilagiri, Ootiya, Udalur, on the down, all towards Kerala side. Okay, okay. Tiruchi proper. Mannachanallur. What is Mannachanallur famous for? Very good. Thuthukudi. Thuthukudi proper Thuthukudi. ரெண்டு தூத்துக்குடி. ஓகே. ஓகே ஓகே. ஏவிஎம் அந்த பூண்டி புஷ்பம் இந்த மாதிரி ஏவிஎம் ஒரு காலேஜ் ஒன்று இருக்குது. ஏடிஎம் நாட் ஏவிஎம் இஸ் இன் பூண்டி, நோ? திருச்சி நீட்டு. சிவகாசி. ஸோ ஃபஸ்ட் டைம் வி ஆர் சீயிங் ஆஃப்டர் மதுரை 1%. ஸோ வி குட் கோ ஒன்லி சவுத் as far as மதுரை. ராசிபுரம், நாமக்கல், அதிகண்ணா. திருச்சி. Okay. So a large fraction of you are from Salem, like that area. Okay. So what I am going to teach you is somewhat in the chemistry domain. It's very similar to quantum chemistry. It is considered as very boring area. Okay. Generally considered as very boring. It is not very boring. It is actually, it can be interesting if you appreciate its importance. How do you appreciate its importance? Okay, I'll start with an example. It may not be very relevant to this lecture course, but from the Indian context you will understand. Okay, so Indian context, understanding anything, why does the world exist? People always ask this. Why does the world exist? Why is it going this way? We always ask. We have no questions or we have no answers, and what we do is each and every part of the world, they try to understand it in their own way. Okay. As far as I know, the Western, so-called Western subjects, of which this is one, they started looking at it only recently. Recently, 200 years, maybe maximum 300 years, right? But much before that, much means 2000 years before, very easily. Okay, Indians started asking, the only civilization in the world which asked this question: why does this earth exist? Why does the universe exist? What is the causation? Because காரணம் இல்லாமல் காரியம் நடக்காது. காரியம் ஒன்று நடக்குது, இங்கே உட்காந்துருக்கீங்கன்னா இதுக்கு ஏதோ ஒரு காரணம் இருக்குது இல்லையா? அந்த காரணம் என்ன? இங்கே காலேஜில் சொல்லியிருக்காங்க, இங்கே போய் படித்தா உங்களுக்கு நல்ல எக்ஸ்போஷர் கிடைக்கும், எக்ஸ்போஷர் கிடைச்சினா மேலே போகலாம். அந்த காரியம் தானே அந்த காரணமும் இருக்குது. காரணமும் காரியமும் ஒன்றோட ஒன்று கனெக்டட். ஓகே. சிமிலர்லி, why does the world or why does the universe exist அப்படின்னு ஒரு கேள்வி நம்ம சிவிலைசேஷனில் இந்த கேள்வி ரொம்ப நாள் முன்னாடி கேட்டாங்க. அதில் 3 fundamental principles they came up with. Okay, this is just to relax you, because 2 o'clock after food you will be like feeling like sleeping. Okay, so the reasons, they came up with 3 things, and the most important thing is from the example. Why does a pot exist? Pot என்ன? களிமண் பானை. களிமண் பானை எப்படி வந்தது? ஒரு படத்தில் பார்த்துருப்பீங்க, உங்களுக்கு நல்லா தெரியும். இவர் வெண்ணிராட மூர்த்தி கேட்பார் வடிவேலு, இந்த ஃபேன் எங்கே வந்தது, டேபிள் எப்படி வந்தது அப்படின்னு கேட்பார், பார்த்துருக்கீங்களா? அதை கம்ப்ளீட்டாக அப்சர்டாக இருக்கும் கொஸ்டின். பட் வி ஆர் டாக்கிங் அபவுட் குட் கொஸ்டின்ஸ். இது எப்படி வந்தது, அது எப்படி வந்தது? ஓகே, பானை எப்படி வந்ததுன்னா, பானை எப்படி வந்தது அப்படின்னா, there is something called நிமித்த காரணம். in our science we say, or what we call தர்க்க சாஸ்திரம், we say நிமித்த காரணம், உபாதான காரணம், சககாரிய காரணம். காரணம் காரியம் சொன்னோம் இல்லையா? ஸோ இப்போ நான் உங்களுக்கு தெரியும், there must be a நிமித்த காரணம், பர்பஸ் இருக்கணும், ஏதோ ஒரு பர்பஸ் இருக்கணும். உபாதான காரணம். ஓகே, உபாதான காரணம்னா எதனால களிமண் பானையை பண்ணுறது. நிமித்த காரணம்னா யார் அந்த பானையை பண்ணுறாங்க. சககாரிய காரியம்னா அதில் யார் உதவுறாங்க. ஓகே, ஸோ பானை இருக்குன்னா பானைக்கு களிமண் தேவை. ஆனால் வெறும் களிமண் பானை ஆகுமா? ஆகவே ஆகாது. யூ நீட் அ பாட்டர், a designer. The potter has to use a wheel. and use the clay, அப்புறம் சுடணும், சுட்டா பானை வருது. இந்த லாஜிக்கை வந்து யூஸ் படுத்தி என்ன சொன்னாங்கன்னா, உலகம் நம்ம இந்தியன் கான்டெக்ட்ல they said the world exists because there is a creator, there is a potter, there is a creator. So you don't have to agree with all these things, but at least there is a thought process. Why does this world exist? Because there is a creator like a potter for a pot. And களிமண், நம்மளாம் தான் களிமண். ஓகே, நம்மளாம் களிமண். பொதுவாக அதுக்கு பிரம்மம்னு ஒரு பேர் வச்சுருக்காங்க. களிமண்ணா நம்ம எல்லாரும் ஒன்று, நீயும் ஒன்று நானும் ஒன்று, எல்லாரும் உள்ளேயும் இருக்கிறது ஒன்று தான் ஒரே அப்படின்னு சொல்கிற ஒரு தத்துவம் அது. பட் லீவ் தட் அசைட், களிமண் ஒன்று. வீல் இஸ் அ டெக்னிக் ஆர் டூல் பை விச் த பாட்டர் மேக்ஸ் த வீல். இதில் முக்கியமான ஒன்று கவனிக்க வேண்டியது, இந்த உதாரணத்தை சொல்கிறவங்க ஒன்று மட்டும் மறந்துடுவாங்க. இந்த தர்க்கசாஸ்திரம் வரும்போது பானையை உதாரணம் சொன்னாங்கன்னா, பானையை செஞ்சவர் எவ்வளோ நாளாக இருக்கணும்? தர்க்கசாஸ்திரத்துக்கு முன்னாடி இருந்திருக்கணும்ல. அப்போ தானே தர்க்கசாஸ்திரத்தில் பானையை பற்றி உதாரணமாக சொல்கிறாங்க. இப்போ பானையை களிமண்ணை எடுத்து ஒரு வீலை செஞ்சு அதை சுட்டு செய்கிற டெக்னாலஜி தர்க்கசாஸ்திரத்துக்கு முன்னாடி இருந்திருக்கணும்ல. அப்போ தானே ஒரு உதாரணம் கொடுக்க முடியும். ஸோ அதே இதை அனாலஜி அப்படியே எடுத்தீங்க போடுங்க கெமிஸ்ட்ரியில். ஏன் நடக்குது? ஒய் இஸ் இட் ஹேப்பனிங்? எதுக்காக நடக்குது? எவ்வளோ தூரம் நடக்குது? அதை நம்மளால் கண்ட்ரோல் செய்ய முடியுமா அப்படின்றது தான் இந்த சப்ஜெக்ட். இந்த சப்ஜெக்ட் என்னென்னா, இட் ட்ரைஸ் டு ஃபிகர் அவுட் ஃபார் ரியாக்ஷன்ஸ் ஆஃப் இன்ட்ரெஸ்ட். மோஸ்ட்லி பீப்புள் டோன்ட் டூ தட். They are supposed to do that. Okay, if you go tomorrow and do research in a organic chemistry lab or an inorganic chemistry lab or a biochemistry lab or some form of chemistry lab, you will directly get into research and hardly anybody really looks into all this whys. Why will come much later. Okay, சும்மா ஏவோட பிஏ மிக்ஸ் பண்ணி என்ன கலர் மாறுதான்னு பார்க்குறதா இன்னி வரைக்கும் மனுஷங்களால் செய்யப்படக்கூடிய research. They don't really get. But in the subject, you need to have a broad way of explaining everything. Why is this happening? Always this. Any science has to address why is it happening? What is the driving force? Can you control it? So this is a fundamental thing we are going to see. And I'm going to make it as simple as possible. Okay. In my belief, this is not a very difficult subject at all. Broad philosophy is something that can be easily understood if you know some very elementary basics. Okay, and from your point of view, most likely this will be useful for when you write a competitive exam, so like CSIR or UGC or GATE exam, or when you go to an interview board will ask you some questions. So to make you comfortable, so that you know the level of confidence can be boosted by listening to these lectures. Now with that, let me start it. So now I started with my BSc in chemistry from AM Jain College, Meenambakam. Then I did a master's in chemistry from IIT Madras. Then I did a master's in technology in polymer science and technology from IIT Delhi. Then I did a master's in science and engineering in polymer science and engineering from UMass Amherst, USA. Then I did a PhD in the same university. I was a postdoctoral associate at Cornell University, Ithaca, New York. This is my educational qualification. Then I've been in IIT Madras from 1995 till date. So I went through assistant professor, associate professor, and I've also done some little bit of work for the institute as a warden, chairman, council of warden, and head of the department, and so on. Okay, so this is my background. I've already listened to your background. Now let's just go to my area of specialization, because you need to know a person. Somebody is talking to you. Who is this person? Tomorrow you have to say, I know him. Okay, for that purpose I'm telling you. My area of specialization is plastics. Chemistry of plastics is what I do. And plastics are formed when small molecules combine, and these are all lines are all covalent bonds to form a long molecule. That is a macromolecule. So that is the subject, plastic. So that's what I specialize in. And to make it a little, and what do I do? What are my current areas of research? I work on two fundamental big natural polymers. Chitin is a natural polymer. Chitosan is a natural polymer which is prepared from chitin. And these are used as biodegradable food packaging materials, super absorbents and gels, So what I do is I broadly work in this area of cellulose, chitosan, chitin, and also nano forms of chitin and nano form of cellulose. So these are all natural polymers, and we adopt green methods to make green methods. It should not be using chemicals like sulfuric acid, sodium hydroxide, DMO, DMSO. You should not use sodium hydroxide. You should not use any chemical that will eventually pollute Mother Earth. Okay. So the crustacean shells are basically food waste products. These are after the crab is consumed, or prawn or lobster or squid fin, shrimp, krill, these are all materials, seafood materials. Once they are consumed, you are left with a shell or a layer, which is like our backbone. That is the backbone of the crustacean. So the crustacean shell waste contains useful polymer known as chitin in about 15 to 40%. Why 15 to 40%? Because there are a number of organisms. In some organism it will be 15%, in some organism it will be 40%. And then you protein about 20 to 40%. Calcium carbonate, because it is a backbone, calcium always serves as a backbone. So that is about 20 to 50%. There are also fats, pigments, that's why some are red in color, some are yellow in color, that is due to the presence of organic pigments, and some trace minerals, small amounts of manganese, iron, tiny amounts. Okay. So these are present, and the whole thing, this crustacean shell or a food waste, is known as biorefinery. Biorefinery means similar to what refinery you get in earth, from which you get diesel, kerosene, petrol, etc., etc., etc. All the synthetic organic small molecules. This biorefinery, it's called because it comes from sea, it comes from biosource. Okay. So this biosource, so one of my students, her name is Devi. So after this, the sea shells can be crushed. They can be crushed because they are hard materials. You can crush them in the form of small tiny particles, and the tiny particles can be treated to get the chitin. Okay. The shell in turn is a beautiful structure. So take a very tiny part of the shell and blow it up, and this is the blown up part of the tiny part of the shell. Then blow it up further, you can see rod like structures, right? These rod like structures are nothing but chitin molecule, which is present like a rod in various angles. Okay. Normally when bamboo sheet is woven into some kind of a basket, the way bamboo sheet is woven into a basket, nature also does it, and these sheets eventually, you can see that as you go down and down in size, it contains a molecule of chitin. This chitin molecule is what interests us. Okay, and it is of value. It has lots of value, and that's why we are interested in isolating this chitin molecule from the shell. Okay. So this is the structure of chitin molecule. Can you see the common structure here? What is a fundamental building block here? Can you identify what is a fundamental building block? Even something you say close to it is enough. You don't have to tell me exactly this is the building block. Glucose, somebody said glucose. Very good. So that's right. So this is a glucose unit. This is a glucose unit. Correct. Anything to the glucose? Glucose, this is beta glucose, right? Second position, what is there? N-acetyl group. So if there was no acetyl group, this will be called glucosamine. Glucosamine is used for cough syrup. Cough syrup, in addition to the active ingredient, use a small amount of glucosamine. It is added, and when you drink glucosamine. Okay, glucosamine, N-acetyl glucosamine, and this is beta position. This is the 1, 2, 3, 4, 1,4 linking. Beta 1,4 linked glucose, N-acetyl glucosamine is chitin. Simple. That is a polymer. So this polymer is what we try to isolate, and from this polymer, if you knock out the COCH3 group, okay, if you knock it out and get NH2 group, that is known as chitosan. The amine form is known as chitosan. The acetyl form is, N-acetyl form is known as chitin. Chitin occurs naturally, chitosan has to be prepared in the laboratory. Okay. So this is the molecule of interest that we are interested, and what we do is, we take one waste, already food waste, To that we add one more waste. So we are waste chemistry people, okay. So whatever waste we do, I love waste, okay, because waste has a lot of wealth. So this pineapple, after you take out all the pineapple, you get a shell, right? This one, the one you see here. Actually, you can see outside fruit shops, this dump waste, okay. So this we simply, this part alone we take, and when we grind it in a mixie, we get a bunch of chemicals all in the form of a juice. It looks like juice, it also tastes like juice, but it is never taken as a juice, okay. Waste, from the waste we simply crush the waste, and the waste material contains chitinase, an enzyme which is present in the juice, bromelain, a protein breaking enzyme, it contains plenty of water, it contains lactic acid bacteria, and also tiny amount of sugar, which is present, that is why it tastes very nicely, okay. So what we do is this waste and the shell waste, so we take crab shell, crush it in a mixie, take pineapple waste, crush it in a mixie, add the two, and that's it, okay. And when we do that, what we do is you get a picture like this, okay. So this is the waste solution, pineapple waste without the fiber, okay, and this is after the addition of the shell waste, okay. This is after some time, this sometime can be even 24 hours, 48 hours and so on, and this is after bleaching. So the bleaching step invariably involves use of hydrogen peroxide. This is not the green part of the chemistry, up to this is only green part, and once you do that, you get something like this, you get whiskers, nano whiskers of chitin. So how do you know it is nano whisker? You use a method known as transmission electron microscopy. In transmission electron microscopy, similar to light microscopy, you use electrons as a photon source. That is, with a torchlight in the dark, you can see all of us, right? Torchlight is a source, light goes around you, I am able to see that you are there. Similarly, in transmission electron microscopy, you use electrons as a source, electron gun as a source, and you shoot at the sample, and the electron goes through the sample, then you are able to see the image of the, like I see or you see me with a torchlight in the dark. Similarly, you can see nano whiskers of chitin. So this is what Devi did for her PhD. So I have given you a little bit about my core heart, where my research interest lies. So if you are interested in research problem like that, you have to do your homework, find out which professor is doing what thoroughly, where are they publishing, and then only you should choose. Don't blindly go and say, this person is okay, this person looks fine, talks fine. Don't go by that. Go by what makes you click, what makes you like something. So that's the reason why I gave you. Now, with that, I will go to the topic. So far, we have spent about 25 minutes. That is okay, because I know that 2 o'clock lecture can be very, very boring. Okay, and when I was a student, that was the time we all slept. 1 to 1:55 lecture is what after food we used to, and get, of course, the teacher used to give us a lot of good compliments, saying that useless people, idiots, you are only fit to take care of buffaloes, all those things we listened to when we were your age. So I will go to the topic. So the topic is basic concepts in, okay. Now, I told you initially about the Tarkasastra 3 fundamental principle, okay. Nimitta Karanam, Upadana Karanam, Sahakarya Karanam. Same thing is valid for chemical thermodynamics. Chemical thermodynamics extracts 3 fundamental principles from thermodynamics, which is a subject in physics, okay. And the first fundamental principle that you need to know is the law of conservation of energy. Till today, nobody has proved it, okay. The only proof for that is there are no perpetual motion machines, okay. There is some machine doesn't go up from up to down and down to up spontaneously. It's the only principle so far. It's not proved, but law of conservation of energy is the first principle in this science, right? Similar to Nimitta Karanam. Second is a transformation at normal temperature and pressure. What is a transformation at normal temperature and pressure? I was born in 1961, normal time, normal temperature, normal pressure, 2025, I am already 64 years old. This is known as spontaneous transformation. Spontaneous has nothing to do with speed, okay. When you look at somebody, I go and hug, spontaneous thing, spontaneous hugging, normally we relate to in terms of speed. Spontaneous is not speed. Spontaneous is nothing to do with speed. What happens without any external provocation is known as spontaneous. Okay, you keep this in your mind all the time. In chemistry, spontaneous means, in organic chemistry, spontaneous is different. In physical chemistry, spontaneous means that which happens without any external disturbance. That is, someday all of us will die. All people born out of a person will die someday. It's a philosophy. Okay, similarly, all spontaneous transformations. So, this a transformation at normal temperature and pressure occurs only if the entropy of the universe increases in the process. Okay, this again, the proof is very tough, really tough. Okay, and sometimes it makes you mad. So, that is why what we do is, when we teach chemical thermodynamics, we do not insist on physical proof from the physics idea. Okay, but we take it as a granted, truth for granted, which is, if something has to happen, the disorder in the universe has to increase. Okay, if I have to walk from here to here, if it has to happen naturally, it's not happening naturally. I am pushing myself. No, I am pushing myself. Is it happening naturally? It's not happening naturally. When I age, it is happening naturally, isn't it? So when I push myself by going this way, it is under some pressure, which is, I want to reach out to this side of the students and that side of the student, right? So if something has to happen naturally, without increasing disorder in the universe, it is not possible for that to happen. So can you think of, tell me one spontaneous example so that we interact here? Any natural transformation? Huh? Rusting of iron, very good, excellent, excellent example. Rusting of iron. Rusting of iron is spontaneous. You need oxygen, you need iron, and normal temperature, normal pressure, Fe becomes Fe3O4. And there is also hydroxide and so on. In fact, I have that example in one last slide. Somebody told me. Okay, according to the second law of thermodynamics, rusting of iron happens spontaneously because the disorder in the universe increases. So we will see in the next class, I will show an example. With that, you will see very clearly why disorder is the reason why everything gets driven. Okay. The third one is, again, somewhat the absolute value of the entropy of a pure crystalline solid at 0 degree Kelvin in its most stable crystalline element is 0. So, third principle is, if there is any pure substance, pure element, there is any pure element in its most stable crystalline arrangement at 0 degree Kelvin, will have an entropy of 0, no entropy, perfectly ordered. Okay. So, these three principles, like these three karanams, you have to understand as take it for granted. We are not going to get into logic whether this physics is right or not. We will take these three as granted. So, that fundamental thing you have to take. Therefore, you can go to chemical thermodynamics, which is karyam. These are the three karanams. So, karyam is what? Chemical transformations and physical transformations that we are going to study. Okay. So, this you keep in your mind. So, in chemical thermodynamics, what we do is, the three laws of thermodynamics are applied to physical and chemical transformations in chemical systems. What I have underlined, look at it very carefully. So, we have to study that it is going to be applied to physical and chemical transformations in chemical systems. So, chemical system is one word you need to take note of, and physical and chemical transformation. Give me an example of physical transformation. Example of physical transformation. Huh? Okay, chemistry. Huh? Ah, very good, excellent. That's exactly what we want. Water becomes, pure water becomes ice, or ice becomes water. Conversely, water becomes vapor, which is happening all the time. That is why in lakes there is a certain amount of loss due to vaporization loss. It vaporizes and there is air current, and constantly from the lake small amount of water will go everywhere. lake's total volume will decrease with time because of this. So, physical transformation, very good. Chemical transformation, rusting you said, huh? Milk to curd is a biotransformation where what happens is that you produce lactic acid, okay. There you have an organism brings about a transformation, it's a biotransformation. But can you think of a chemical transformation? Rusting you already know. One more chemical transformation. Simple, that is why you do go to the lab. Huh? Carbohydrate. Photosynthesis is a chemical transformation, correct? Electron transfer takes place on the leaf due to magnesium porphyrin complex, and you take carbon dioxide, it goes through 54 steps before it makes glucose. Okay, really wonderful that somebody really studied it in such depth and found out each and every step, identified the 54 steps, and that automatically led to the idea of can we have synthetic synthesis, that is, can we do photosynthesis in the lab with light, okay, because you understood the mechanism. So, mechanism was instrumental. So, chemical, physical transformation and chemical system. So, physical transformation, solid to liquid melting, liquid to vapor boiling, and there are many more. Chemical systems is reaction, okay. Chemical systems are naturally, now I will now use a blackboard. So, you need to picturize, always model. If you are asked a question also, always try to model it in your head. Once you model, answering becomes very easy, okay. So, I am going to just start with, this is the okay. So, what is this? This is a flask, no? Erlenmeyer flask, you heard of flask? Conical flask, okay. So, call it conical flask, no problem. Conical flask, and the conical flask has something inside, okay. That something inside can be a gas, it can be a liquid, or it can be a solid, or it can be a mixture. Suppose I put ice, it will be a mixture of ice solid or water solid and liquid water and vapor, 3 phases will be there, right. Suppose I use wood, it is a composite material. So, you will have only wood, solid alone, 1 phase will be there, right. Suppose I use hydrogen gas, only 1 hydrogen gas will be there. So, this can be gas, liquid, solid mixture, and that is the content. As far as chemistry is concerned, we always focus on the stuff inside, okay. So, this whole thing inside, this whole thing is called system. Why is it called system? Because we are interested in the transformation, chemical transformation or physical transformation. So, that is called system. Systems can be 3 different types, okay. Okay, you must have studied this. How many types? Open, closed, isolated. What happens in an open system? Very good. So, conical flask I will rub off. In open system, mass and energy exchange. In a closed system, energy exchange alone, there is no mass exchange. This is no mass or energy exchange. You never encounter this. The reason why we have it is, in physics, all the laws of physics, the 3 karanams I showed you, always it starts with an isolated system, which never exists. So, what we do is, for a real system, we say this can be considered as an isolated system. When in this, if you consider for this classroom, for example, we are the system, surrounding is outside the class, and we say stop with chemistry department, that is the isolated system. So, isolated system does not exist, but for theory purpose, physics, where the laws came, they are applicable for isolated systems. So, we treat open system and closed system as a special case of an isolated system. So, this is not normally, we do not see in chemistry. In chemistry only two things, okay. We see open system and closed system. So, when you do a reaction in a beaker, open beaker or an open conical flask, okay, then that becomes a open system. We normally do not do that, everything is done in a closed system only, because you want to confine everything to a small region and you do not want it to be going out everywhere. Loss of mass is not something that you do not want, right. So, as far as chemistry is concerned, what will you do? Invariably, only closed system will study. So, whatever I am going to tell you now from thermodynamics 3 karanam, right, the karyam is chemical transformation or physical transformation. There again we are restricting it to closed systems only. Open system is difficult to deal with, maths is quite hard. So, closed system is what we do in actual reality, so we stick with closed systems, okay. So, closed system, so matter inside there are what is known as equation of state of a matter, this is known as state of a matter, right, state of matter. State of matter we have gas, liquid, solid, okay, and matter invariably is related by what is known as the equation of state. Matter, if it is any matter, there is an equation of state. For example, PV equal to nRT is the perfect gas equation. There are other equations of states, we do not use them, okay. We are happy with perfect equation of state, it is very simple to deal with. In real stuff you have to use real equation of state. You will never encounter in any book. So, close your eyes and say whether it is perfect gas or non-perfect gas, PV equal to nRT, because it is very difficult. There is a small correction factor we add and it is all set, but perfect gas equation is more than adequate. So, open system, closed system. So, we are going to stick with closed system, right, and then we are going to see only perfect gas equation. So, any transformation of state, whether it is physical transformation or chemical transformation, what brings about the transformation? What are the factors that bring about the transformation? Any transformation or rusting of iron, what is the factor that makes it happen? What factors make it happen? Oxygen, okay, that is a gas which is present outside. Anything else? Suppose I add salt to it, will the rusting of iron take place faster or slower? Faster, okay. Sodium chloride is used as a catalyst. See, Siachen glacier, when we had a war in Siachen, and also, you know, what is the other glacier where we had a fight? Siachen and not able to recall immediately. Kargil, okay, the glacier, those are freezing cold. Freezing cold is really freezing cold, you can't really, right. So, soldiers at that height, they have to go to that height, low oxygen, no, it's freezing, really freezing. The way they keep themselves hot is to use iron powder. They use a small amount of iron powder, they will be given iron powder patch and sodium chloride. So, in the shoes, another part inside the jacket, they will mix A and B. A is iron powder, B is sodium chloride, mix it up, it heats up. Without sodium chloride, it is very slow. Iron to iron oxide is an exothermic reaction. But it won't give enough heat unless you add sodium chloride. Sodium chloride makes it fast. So, sodium chloride, so we saw that you can vary the composition, that is what you said by oxygen, other is by using a catalyst. Anything else? What are the variables? Very good, excellent. Now you will have no difficulty with thermodynamics because, so what are the factors that make a transformation happen? Variables, okay, variables in your hand that you can use to make a chemical or physical transformation take place. The variables are pressure, volume, temperature, composition and catalyst. So, we are interested in some transformation here, whatever be the transformation. I am going to write A simply, B, and I am going to write gas. So, you have to define the state. A to B transformation is taking place inside the flask. It can be a physical transformation, it can be a chemical transformation, but it is influenced by variables such as pressure, volume, temperature, concentration, catalyst. So, closed system, and that is it. Now, if you want to understand anything about this, what is happening here? Can I bring down the boiling point of water? Can I increase the boiling point of water? Can I make this transformation N2 plus 3H2 becoming 2 ammonia? How will I do it? That is a question that chemical thermodynamics helps us to understand. How will you push the reaction so that you maximize the yield? Okay. Unless you know the principles of chemical thermodynamics, it will not be able to tell you, rationalize it. You can always get a result and write it in a paper or somewhere notebook, but you have to rationalize anything and everything and see whether whatever you rationalize can be tested under some other condition, or you can predict the results. What is more important in a model is always prediction of a result. You should be able to predict a new situation in which what will happen. So, like astrology, right? Just giving an example, it is not science. So, the predictability element of any theory is very important. Unless it can predict in a new situation, the theory has no meaning. Theory can explain what happens, lot of white hair, that can be a theory, but it should also predict. Somehow, another 10 years from now, will I have everything completely gone or not? If it does not predict, no use. Theory has to have 2 dimensions. Explain what is going on and have this so called important predictability dimension. X years from now, X minutes from now, what will happen? So, without that, theory has no meaning. So, that is what we are going to do now. So, system consists of gas, liquid, solid and mixture. Variables already we have seen, normal temperature and pressure. Okay. Sublimation of iodine. If I have iodine here, iodine will spontaneously sublime into the vapor phase. It is used in a technique known as thin layer chromatography. If you do organic chemistry, after a chemical transformation, you take the product and place it on a silica gel plate. Okay. And then after placing it on the silica gel plate, you take the sheet and place it in a bottle containing iodine. Iodine will sublime and react with the organic compound to give brown color. Okay. So, that is so sublimation of iodine in a closed system is a physical transformation. So, variation of temperature, pressure, concentration and sometimes even light, electromagnetic radiation, which will come under energy. So, catalyst, these are the factors which should be able to vary and address what is going on. Now, let us picturize it. I have already picturized it on the blackboard for you. So, now let us deal with specific examples. Okay, contemporary topics. If you talk about a topic and if I give you some old 1890 chemistry, you will not be interested. You will think I can read it in a textbook, YEC, talking about 1890. So, what I will do is try to make examples or take examples from contemporary topics, so that you see the relevance of what I am trying to attempt to teach you in a modern context. Okay. So, we will see now it is already another few minutes. Okay. We can take a break and then reassemble. So, specific example will actually take you to understand this very important topic. What is most important topic in chemical thermodynamics is combustion. Combustion is reaction of an organic compound with oxygen to give energy or heat plus carbon dioxide plus water. The reason why I am speaking to you now is I had food at 1 o'clock. The food has been broken down by enzymes in the body into small molecules, and from the molecules you get glucose. Glucose has been transported to the cells, and in the cell glucose is getting converted to carbon dioxide, water, and lot of energy, plenty of energy, 55.4 megajoules of energy per mole. Okay, so lot of energy comes in the cell. The cell should burn, no? So much of energy, 55.4 megajoules per mole. In cell, typically micromolar concentration of glucose will be there. If it is 1 mole, all cells will burn black color. After eating food, you will become black, burn away. You don't become black because every cell contains only a micromole of glucose, nothing more than that. So 55.4 megajoules per mole. So per micromole it is 55.4 joules. Still 55.4 joules is a lot of energy. Every heartbeat requires 1 joule. That motion requires 1 joule of energy. 55 joules for a cell is a lot of energy. So it is not given directly in cash. It is given only in kind. There are multiple ways. It will break down stepwise fashion. So I am able to get energy to speak to you. Breathe. I am able to breathe. My heart is beating, and all because of this fundamental reaction, which is reaction of carbohydrate or glucose with oxygen to give carbon dioxide, water. Okay, and anything and everything in this earth that we think we are in control, whatever happens is due to the reaction of a fuel with oxygen gas to give carbon dioxide gas, water gas, and heat. So what are the applications? For example, transportation, air transportation, road transportation uses lot of fuel. What is a typical fuel in a car and two-wheeler? Diesel, petrol. Petrol, what is a hydrocarbon associated with petrol? Typically petrol. Octane, very good, excellent. So diesel is a little complicated, we won't get into. What about today's two-wheelers and autos? They use compressed natural gas. What is compressed natural gas made of? Methane gas mainly. Mainly methane gas. Then comes a little bit of ethane, even less of propane, even less of butane. Beyond that is a liquid. Okay, these gases, but mainly methane gas. So that's what all auto, you see nowadays petrol bunks are becoming auto bunks, gas bunks, liquid natural gas or compressed natural gas, one of the two you will get. Liquid natural gas normally is used for transporting from places where gas is produced or extracted, like Qatar to India it will come in liquid form, but when it comes to bunk it will be in the gas form, compressed gas form. So this transportation, air and road transportation uses fuel. Manufacturing and production of goods, any energy, any goods has to be produced, it has to have energy. Without energy nothing can be produced. Where will the energy come from? It has come from combustion. Okay. Sometimes it comes from electricity. But where does electricity come from? Burning of coal, burning of gas. Hydroelectric power is rare. Okay, in India, right now about 1/3 right now, about 30% is from wind power and solar power. Still 50% plus is from burning coal and gas still. Okay, it's not a small number by any means. Okay, and heating in homes in cold climates like Delhi, Himachal Pradesh, Jammu Kashmir, etc. There they use fuel. Without that, daytime they cannot even live in the house. It will be so cold, especially in the months of December, January, and February. So, how can chemical thermodynamics help in this? Okay, now what we can do is how much of useful energy can be extracted as work and how much of heat is likely to be generated and how to optimize that. Okay, I am going to give you a real example with an auto. Okay, you can also do the calculation on your own. Tell me if my calculation is correct or not. Okay, I am going to shortly give you that example. So, purpose of chemical thermodynamics when it comes to fuels is how much of this fuel can actually give me the necessary positive useful work, whether it can give me enough heat if my purpose is to heat the house, how much heat energy it will give, how much of energy is not available, that is also important. Can I optimize it? How will I optimize it? Without thermodynamics, you will not, chemical thermodynamics, you will not know what to optimize, where to play with, okay, that is where it plays a very important role. So, now we will take a small break, okay. Now with this and this example will close. It is very important for your generation because you are going to be the people who will be living 50 years from now when India will be a very highly developed state, okay, in terms of economics, okay. Here is an example. Can you see what these are? I took it, wherever I have taken the source, I have given the reference. It's an image, is internet. These are planes. Last night, if you had taken this picture, okay, which is available for all of us to see, no planes over Iran. No planes over Iran because no fly zone. Okay, no planes over Israel, no fly zone. No planes over Jordan. You can see this in internet if you are interested. So, but if you see it, any point of time, now currently throughout the globe, there are plenty, hundreds and hundreds of aeroplanes flying. Most inefficient way of consuming fuel because we are greedy people. People are extremely greedy. I want to go distance of 300 kilometers Chennai, Bangalore in half an hour. I am willing to spend 1.5 hours in traffic jam here, 2 hours in traffic jam there, half an hour flying, total time is 5 hours. The fuel consumed for me when I calculate with respect to road takes 1/5 the fuel. How much carbon dioxide I contribute by flying? About 10 times the carbon dioxide that I get from road travel, right? So, this air travel is the most, it is the fastest in terms of time, it is the fastest, but in terms of energy efficiency and pollution, it is a worst form of travel and the whole globe does it in large scale. So, that is why fuel is very important. Why you have to study fuel, alternate fuels, green fuels, how to make the fuel more efficient, it is important to study this problem, okay. And as though this is not enough, there are hundreds and hundreds, not even thousands, not thousands probably, of planes flying over. So is the ships, all the ocean, entire ocean in the world, okay, full of ships. And what are they doing? They are transporting oil. If you see the place of origin, invariably Strait of Hormuz. Strait of Hormuz is where we have Saudi Arabia, United Arab Emirates, Kuwait, all the Iraq, Iran, all the oil, about approximately 40% of the world's oil comes from that region, okay. There are so many ships carrying oil throughout the world, South America, North America, Africa, any place. If you take a satellite image, ocean is full of like mosquitoes outside a place at night, like 6 o'clock, when you go outside any house or any restaurant, 6 o'clock, full of mosquitoes. Why are they coming? Why flies are coming in the morning? Because they have something to do, no? Like that, our seas are full of ships, our space is full of planes, all are burning fuel, all the time, 24 hours, 7 days a week, 365 days a year. For the last 50 years or so, okay, it is only increasing and increasing, it is becoming more because we have doing this most important thing. Every country worth its name makes oil now, okay, except China, not much, India, not much, big Russia, tons and tons and tons of oil, okay. So is North America, so is South America, some places in South America. Africa only gases, not oil, not much, right. So what you have is every place, I don't know if you see a lot of YouTube videos, you can see in places like Azerbaijan, every next door will have, one will be house, another will be this, and next door will be another house. So it looks like as though like we have wells in our houses to draw water, these people have oil wells from which they constantly produce oil. So this one then comes to a place like Chennai Petrochemical Refinery, oil from the ship and gets converted to all the fuel, right. This is a picture So that's what happens, and at this point I will stop.
SwayamPrabha. Digital India. Educated India.